Converting light, that is photon, into electricity, that is voltage, by using solar cells is popularly known as solar photovoltaic cells or solar PV cells. A large majority of solar cells are made of the material called silicon, but a new generation of solar cells are being made using special solutions made of certain organic and inorganic material, which is the focus of this program. A large number of national laboratories, science managers and innovators over the last 3 decades have worked to open many a window to the sun.
Well, India is very good in the photovoltaics fundamental research, and that's partly because over several decades really India has put a lot of effort into physics, material science, chemistry, all of which are very, very important for photovoltaics.
Among countless novel approaches in research and development on solar photovoltaic cells, some milestones clearly stand out. They found out novel solar cell processes. They created chemical stations that worked automatically. They set up molding areas. And when it came to coating the solar photovoltaic cells, they designed equipment that did the job exceptionally well, besides developing a host of other technologies. And all of this claims some new space. When the first Indian scientific expedition in 1981 went ahead with special solar photovoltaic power packs. The unmanned offshore oil well counted heavily on solar photovoltaic power systems. Foldable modules of solar photovoltaics breathed life into Everest 1984 expedition, besides other countless achievements. Well, yesteryears they were, of course, but today in this program, taking you to the Indian Institute of Technology at Mumbai, we would attempt to present for you some of the recent advances that are being made in India. The most commonly used renewable energy source is solar energy. But how is solar energy used to generate electricity? A photovoltaic or PV system is used to convert a solar or light energy into electrical energy. The basic component of the PV system is known as the solar cell. A single solar cell has the capacity to produce about 0.5 volts of electricity. A solar panel or solar module is the combination of several solar cells connected in series to generate usable voltage. A combination of solar panels connected in series is known as solar array and can be used to achieve required current and voltage. But how does the solar cell work? The generation of electricity on exposure to sunlight is known as photovoltaic effect. The photoelectric effect was first noted by a French physicist, Edmond Becquerel, in 1839, who found that certain materials would produce small amounts of electric current when exposed to light. In 1905, Albert Einstein described the nature of light and the photoelectric effect on which photovoltaic technology is based, for which he later won a Nobel Prize in physics. The solar cells are made up of semiconductors, mainly silicon. These comprises 3 layers. The top layer, called the N-type layer, is comparatively thin and contains a high concentration of electrons. The bottom layer, called the P-type layer, contains high concentration of holes. The junction is called NP-N junction. The electrons on the NP-type material try to reach the P region, creating a negatively charged layer. Similarly, the holes of the P-type try to reach the N region, creating a positive charge layer. This region between the two layers is known as the depletion region of the semiconductor. Light penetrates the top thin layer to reach the depletion layer. Due to the deficiency of charge in the depletion region, it contains neutral atoms. The neutral atoms are broken when the photons from the sunlight strike the depletion layer. This knocks the electrons from the neutral atoms, leaving behind the holes and leaving behind the free charge carriers. Then the electrons move towards the N-type layer and the hole towards the P-type layer. Thus, an electric field is produced in the depletion region. On connecting a circuit, the electrons flow through the circuit, generating electricity. To achieve Atmanirbhar Bharat goals through renewable source of energy, India is gearing up to cut carbon footprint by 30 to 35% by transforming parts of the energy sector into clean and green energy powerhouse. India ranks third in installed capacity of solar photovoltaics after China and the US in the years of 2016 to 2019. This is where the story unfolds. Some of the newer materials and novel ways of making solar photovoltaic cells at this Department of Energy Science and Engineering, as well as the National Centre for Photovoltaic Research and Education Lab at IIT Bombay, are pointers enough of what is new in solar photovoltaic research today. When we met the research group led by Dr. Shaibul Sarkar at IIT Bombay, Dr. Neha was attempting to find better ways of making the novel flexible solar photovoltaic cells last longer and be more stable by using a technique called atomic layer deposition. They prefer calling it encapsulation. Working under vacuum, Dr. Rosa was almost done with putting together a high-voltage solar photovoltaic cell with fairly good current. Though she is also capable of creating a solar PV cells with high voltage but low current, which could be used in number of special applications. And here, Anand Selvan was glad for getting very close to figuring out a way which just might allow us in future to manufacture solar photovoltaic cells out of special solutions and not by using the conventional silicon. Dr. Shaibul Sarkar would share some of the secrets about it later in the program. A closer look reveals the trial by fire that these researchers have been through in reaching the stage of which you just took a quick look.
It is the kind of a thing that is called the perovskites. So we had worked on this kind of a perovskites material, okay, which are basically the thermochromic. It's not the photochromic, but it's a thermochromic. So as a function of the temperature, it changes the color. We are not basically competing with the decades of silicon technologies, but we are going to a niche area where this particular technology is needed. The thing that what we are talking about in the lab, where we are talking about the thermochromic devices, the temperature goes up to 45 degrees centigrade, it will turn black. And when it turns black, it absorbs the light, and when it absorbs the light, not only you're inside the house, it will get cooler because that's the greenhouse effect you are basically eliminating. And not only that, they are able to use as a kind of a devices which can generate the power. So for an example, any northern part, let's say Delhi for an example, okay, or anytime Rajasthan, even Gujarat, Madhya Pradesh, where the temperature summer goes pretty high, 40-42 degrees centigrades, and the glasses goes much higher temperature than that because of the direct sunlight, that can be used directly as a kind of a curtain, and which goes black, absorbs light, generates power.
Well, of course, solar energy, you really are talking about two two different types of solar energy. One is the photovoltaics, the other is the concentrated solar power. In both of these cases, we in India have a reasonably good R&D base, and in solar thermal, we actually have a lot of very interesting activities going on.
The International Energy Agency indicates that global solar trends have turned positive. Photovoltaics, that is PV, are now expected to lead capacity expansion in the global power mix in all its 5-year forecasts. And the agency estimates that if climate change goals as set by the Paris Summit are to be met, solar PV capacity has to become the world's largest installed capacity by 2040. Accounting for almost 25% of the total energy consumed.
The next-gen manufacturing process which we would like to look at is broadly the roll-to-roll manufacturing. So a roll-to-roll process is something like what is done in printing of newspapers. They have a large roll of paper on one side, it goes through the printing press and gets collected on the other side. Now similarly that in between, instead of printing the regular print, you would actually print the photovoltaic materials which would result in a solar cell at the end.
We would like to make a technology which is reliable, stable and recyclable as well as cheap. So therefore, for an example, if you think about it, that you are going for some hiking or somewhere where you go out, you get the cells, you just stretch it out, just like a curtain, you put it on you make it a device, your things can work, and you come back. Even if it goes bad, we can recycle and give it a fresh cell back to you. It's just like a kind of a mobile battery charger. Another example could be the army, who go to the Siachen or to the border areas. They can use these devices. They can just take it out because it is flexible, so therefore it is a lightweight. Let's say they are coming back after 2 months from the advanced area. They can give us back to the provider. They recycle the things and they will give it back the same, the same hardware back to them, so that they can reuse it.
$5,000 hours may seem like a long order, but nothing stops this research team from trying. And that was what Dr. Neha was doing while working on encapsulation using atomic layer deposition, which allows solar cells to be created below 100 degrees and without the use of multiple vapor deposition technique, using expensive machines as in the making of conventional silicon solar cells. Today, it is possible to make solar cells from only exclusive solutions. It's like painting a solar cell. And because you can witness the cells here being deposited atom by atom, it makes the cells sit more firmly and therefore become more stable to last longer. Solution processable solar cells would mean that exclusive solution would be the raw material for manufacturing the new age flexible solar photovoltaic cells. Atomic layer deposition essentially means the deposition of the thin films of a variety of materials by a procedure called sequential chemical process, where the number of reaction cycle determines the thickness of the film. This is done to achieve accurate thickness and uniform surface of a material. It occurs in a specially designed atomic layer deposition, that is ALD reactor. The reaction starts with precursors entering the chamber, which react with the substrate, that is the base. A thin film is deposited with each reaction cycle. An example is the deposition of titanium dioxide on silicon substrate. Till date, atomic layer deposition is commonly used in academic laboratories and on a variety of commercial industries, starting from tissue engineering to solar cell manufacturing units.
We developed a technology where everything can be made below 100 degrees centigrade. Therefore, we can use the polymer to make the efficiency of as high as of 21%.
Well, it may not be as easy as it sounds. The substrate, that is the base on which the novel flexible solar photovoltaic cells are placed, are expensive to come by. And therefore, the group here at the Center of Energy Science and Engineering at IIT Bombay are finding out ways to surmount it.
The substrate that what we are using, are very costly. And therefore, if we can reuse the substrate again and again, after, therefore we can make the technology much more, viable and much more cheaper.
The secret in the solution that holds the promise of making solar photovoltaic cells cheaper, flexible, reusable and stable resides in it being constituted of an organic as well as inorganic components.
So the organic counterpart actually makes a lot of difference to the property of the material. That makes this material very low temperature processable. So we can make the solar cell which is below 100 degrees centigrade. That makes the production process substantially cheaper.
And to do this, the energy as well as the infrastructure required would be a lot less, resulting in a lesser energy payback period and a reduced money payback period as well. Though the excitement is new, perovskite has been known to science since at least the 1830s, when it was first identified by a German mineralogist, Gustav Rose, while prospecting in the Ural Mountains, and named after Russian mineralogist Lev Perovsky. In the following decades, synthesizing the atomic structure of perovskite became easier. But it was not until 2009 that Japanese researcher Tsutomu Miyasaka discovered the perovskites can be used to form photovoltaic solar cells. And though all of this holds many a bright prospect, the ground truth of silicon loading over the technologies at the moment can hardly be escaped.
Reliability is very important because the modules once installed have to be out in the field for 25 years. That's a very long time and it's a very demanding time. It's also demanding in many of the climatic zones in which the modules are deployed, like for example Rajasthan in India or Arizona in the US.
Reliability indeed is very important because the modules once installed have to be out in the field for 20 years at least. And that may be why they are attempting to see how best it could be achieved out in the field.
What we are doing is we are trying to calculate soiling loss of Mumbai, and we do this. We have installed solar modules of different technologies. So you can see bifacial modules, monofacial modules. They are multi-crystalline monofacial modules, and these two are monofacial modules, monocrystalline. So we clean one module of each module set has two modules. The cleaning is done at the evening time after the sun sets. So we don't disturb the data at all. The data of these, so we calculate power, voltage and current. We also calculate the solar radiation by the pyranometer which is there. We also calculate the ambient temperature. So we take some weather data to do some translation or some corrections in the data that we are getting. This data is stored in 1 minute interval of time. That data logger serves the data to the server directly and we can access it in our lab. These all modules are at a tilt. So the tilt is 19 degrees, which is the latitude of Mumbai. So ideally always the modules are at the latitude tilt of the place. And those two modules you'll see specifically are at 90 degrees. So they are vertically mounted.
With solar photovoltaic technology evolving, costs coming down and grid connectivity improving, the dream of universal access to clean energy is becoming more real.